Hello everyone, welcome to the lesson on energy and work done. Now in this video, we are going to focus on energy conversion. So at the end of the lesson, you will have a better idea of the relationship between energy and work, and you also understand more about what does it mean when we say that energy is conserved. You will also be looking at a few situations or objects that convert energy from one form to another. So let's begin. Now, when energy is done, when work is done, energy is transferred from one object to another or converted from one form to another. So exactly what it means, let me use this javelin thrower as an example. Now, when the javelin thrower throws the javelin, she transfers her own kinetic energy to the javelin. So of course the javelin goes out this way, right? So the energy transfer is from the thrower herself, from herself to the javelin. Okay, so I just try to draw a javelin, okay, to the javelin. And what is the energy conversion that takes place? Well, the javelin thrower is able to throw the javelin because she has the energy. So where does the energy come from? The energy comes from the food that she eats because within the food there is chemical, potential energy. So during respiration, the chemical potential energy in the food is given out and it provides the body with energy. So from chemical potential energy, it will be transferred to kinetic energy of the thrower. And then when she let go of the javelin, it goes into kinetic energy of the javelin, right? So from the thrower, it goes to the javelin. So this is an energy transfer, and we also see energy conversion over here. So in doing all this, we say that work is done because there is a force exerted. Okay, maybe I'll just use a different color that is clearer for you. Mm, okay, so basically there is a force that's exerted and then the javelin moves in the direction of the force. So that's why we say work is being done. So in this work done, energy is transferred from the thrower to the javelin and is converted from the chemical potential energy to the kinetic energy of the javelin. And of course, if the thrower has more energy, she will then be able to do more work because the javelin would then be able to travel further and she's also able to give more force, right? So because when we look at the previous part of the lesson, we know that work done is force times distance. So with more energy, let's say the javelin thrower will have more force and the javelin can also move further. But during this whole process, where the javelin is being thrown out, there is no energy that has been produced or destroyed. And this is what it means when we say that energy is conserved. So, what it means by conserved is that the total amount of energy in this whole system remains the same. We'll look at the next question, we'll look at the next example to understand what does it mean when we say energy is conserved. So one of the most important concept in this whole chapter of in this whole chapter of energy is the principles of conservation of energy. So basically, there are two things said here. Number one, energy cannot be created or destroyed. So the total amount of energy in on Earth actually is the same, but energy can only be converted from one form to another or transferred from one body to another. Now, I'm going to use this car as an example to illustrate. Now, when a car is being parked in the car park, um, it is not moving, so there's no kinetic energy, and let's assume this ground level, so there is no gravitational potential energy as well. But within the car, we know that you to move a car, you need to pump petrol, right? So for petrol, there will be chemical potential energy. So this car park stationary has chemical potential energy. And I'm drawing a box over here to show that this is one whole system because actually when we say energy is conserved, it's not just within the car, but basically it's this whole system, this whole area around the car as well. Now, if the driver goes into the car, starts the car, and then the car starts moving. Let's take a look at all the energy that's involved here. Definitely, we know that the car is moving, so there will be kinetic energy. And in order to move the car, you actually burn the petrol. So and of course, we also know the heat. The car gets a bit hot, so a bit of heat. So there's heat produced, and of course, some sound may be produced because it's noisy. The heat is also from the friction with the ground. But at the same time, let's not forget that there will still be some chemical potential energy, but it's going to be less because there's less petrol left, right? Because you are driving. So I'm writing this word a little smaller. Now, if you look at the initial amount of energy, is chemical potential. The final amount of energy, there's chemical potential, there's kinetic, there's heat, there's sound. Because energy is conserved, these two amount is the same. So if let's say I have 2 kilojoules of chemical potential energy, even as the car is moving, the total energy for the car and also some of the heat that is present in given out to the surroundings. So this whole area that I have boxed up, the total energy within this whole area is also 2 kilojoules. So this is what I mean by energy being conserved because it is not created, it cannot be created, it cannot be destroyed. Let's look at some other examples. Now this archer is pulling the bowstring. When the reason why this archer has the energy to pull again is because he would have eaten food, and then the body's respiration process releases the chemical potential energy in the food. So chemical potential energy, actually, I think this should be more appropriately in the food. It's converted, chemical potential energy in the food is converted to uh, kinetic energy of his arms, right? Because now he has energy to pull his arm backwards. And in doing so, he is also pulling the bowstring backwards. So then to kinetic energy of the bowstring. And when the bowstring is being pulled backwards, you are actually extending it. Now we know that the bowstring is elastic object. So when you are extending the bowstring, you actually help to convert the energy into elastic potential energy in the bowstring. So therefore, if you look at this, the whole energy conversion is from the chemical potential energy of the foot to the kinetic energy of his arms and is transferred to the kinetic energy of the bowstring and finally is converted to elastic potential energy in the bowstring. And what we see here, this part, is what we call overall energy conversion. So take note, this is called an overall energy conversion. Sometimes the question may not need you to talk about all the small, I won't say small, but all the intermediate energy conversions, like what I've written in blue here. All they want to do is where does the energy come from? And eventually where does the energy lead to? So you only need to write the initial and the final, and this is what we call overall energy conversion. Okay, and of course we know that when you are exerting a force and then the bowstring moves in the direction of your force, then work is done, right? So you can see that work and energy are very closely related. You use work to actually transfer or convert energy. Let's go on to let's continue with the example of the archer. So now he releases the energy and then the bow moves forward. Again, if I were to ask for the overall energy conversion, you only need to write elastic potential energy in the bowstring converted to kinetic energy in the moving arrow. So you can see that there are two things happening here. There is a transfer of energy from the bowstring to the arrow. At the same time, there is also a conversion of energy from elastic potential to kinetic, right? So this is the overall energy conversion. And of course, when we do when we when we convert and we transfer the energy, work is being done because the force exerted cause the arrow to move a certain distance. So remember, so work done is force times distance. Energy is also being converted. We see energy conversion in our daily life. So I'm going to go through a few common examples of energy conversion. So this is one. Let's go through some electrical appliances first. So electrical kettle. So what it does is you input electricity and then the kettle gets hot, it boils the water. So again, the energy conversion is electrical to thermal. And the energy from the electrical energy in the wires go into the kettle is transferred to the thermal energy of the water. The television, again, you need to give the television electrical energy, and the television will then convert this electrical energy into light and sound. It is going to be the same energy conversion even if I were to ask you for energy conversion in a laptop, because a laptop, same thing, it takes in electrical energy and gives out light and sound energy. Let's go on to other examples. This is the charging of a rechargeable battery. It will be the same answer as well. If we are talking about charging of a handphone, charging of a handphone, a laptop, because in all this equipment, there is also a battery inside that you are charging. Okay, so whether we're talking about all these type of batteries or a handphone or laptop, the energy conversion is the same. So in order to charge your handphone or laptop, you need to plug it to electrical source. So there will be electrical energy. And the electrical energy will go into your cell, laptop cell, handphone cell, or your batteries here. So electrical energy comes in and it will cause a chemical reaction to happen inside this cell. So when a chemical reaction happen, you will form chemical bonds and you are storing the energy inside these chemical bonds. So that's why it's chemical potential energy. And when you start to use this cell, then this chemical potential energy will be released into electrical energy. So charging a battery and using a battery, the energy conversion is opposite. So when you charge a battery, you give electrical energy and you are storing it as chemical potential. But when you are using a battery, then it is from chemical potential to electrical energy. So which is the example that's illustrated in example 4 right now. If you are using a battery operated torchlight, so to first use this torchlight, you need to complete the circuit. So the chemical potential energy in the battery will then be converted to electrical energy inside this that will be flowing within this torchlight, and it will cause light and heat to be generated. And final, no, not final yet, but question, example 5, a person running, same thing. Each time a person is running, a person is lifting something up, a person is pushing something, it requires energy from the food that the person is eating. So that is again chemical potential energy. So remember, chemical potential energy, there are three sources. Food is one of the source. Fuel, anything you burn, petrol, paper, wood, as well as battery, right? So these are the three categories. So when you see these three objects, likelihood you will have to start your energy conversion with chemical potential energy. So when the person is running, this chemical potential energy from the food that he ate will be given out by the body and converted into kinetic energy. And that's why you can run, lift, and push. Burning a piece of paper, again, a paper is something that can burn, so that's a fuel. So chemical potential to thermal energy plus heat. This is the process of combustion. So it will be the same energy conversion if we are talking about burning of petrol or burning of a piece of wood. And Then we got photosynthesis. Now, plants can only photosynthesize in the presence of sunlight. So when the sun shines on the plant takes the light energy from the sun. This is the supply of energy that the sun has. So the sun takes this, sorry, the plant takes this energy, use it as a source of energy to make food. So photosynthesis basically means making food, right? So when we are making food, making the sugar, the starch, you are actually forming bonds. So you need energy in order to do that. So forming chemical bonds to make your food. So you use the energy from the sun. And then when these bonds are formed, you form your sugar, your starch, then the energy is stored inside these bonds, right? So they are called chemical potential energy. And eventually, when you eat this food, then it will release the energy and then allow you to run and do work. This little boy drops a ball downwards, and when the ball is high up there, uh, in this position, the ball has gravitational potential energy. There is no kinetic energy because the ball is being held by by the boy. He did not drop, he's just holding it, so the ball is not moving at all, so there's no kinetic energy. Remember, kinetic energy is only possessed by objects that move, but gravitational potential energy is possessed by any object that is above the ground. So this is ground level, so definitely there's a certain height, right? So this ball has GPE, gravitational potential energy. Now, when when a boy drops the ball, the height of the ball gets, as the ball approaches the ground, the height gets lower and lower. So we can say that GPE decreases, okay, because gravitational potential energy depends on the height. So as the height decreases, GPE decreases. Now, what about the kinetic energy? Initially, there is no movement, so there's no kinetic energy, is zero. But as the ball is moving down, its kinetic energy increases. Why is that so? Because anything that you drop, let's say this is the earth, anything that you drop near the earth is going to move faster and faster as it approaches the earth. And this is due to gravity. So the kinetic energy will increase because the speed increases. So therefore, at this point, your speed may be this amount. At this point, your speed will get bigger and bigger and bigger. All right. So the speed actually increases as you drop towards the ground. So whatever that you have lost in GPE will be gained as KE. So this whole dropping process, the energy conversion will be from GPE to KE. Okay. But I want you to know that as it drops, gradually there will be lesser and lesser gravitational potential and then more and more kinetic. But at any point, let's say here or here or even here, there will still be some gravitational potential energy, just that it gets lesser and lesser. The only point where there's no more potential energy and only kinetic is just before it hits the ground. Okay? So that brings us to energy conversion of objects that's being thrown up and down. So let's, just now you have looked at the energy conversion of a ball being dropped. So now let's take a look at energy conversion when a ball is thrown upwards. One thing to take note is that when you drop a ball, initially there is no kinetic energy because we drop a ball. Okay, so dropping means that there is initially, so the initial speed is zero because you're holding it and you just let go, you dropped it. But when you are throwing something upwards, the object cannot move up unless you push it up. So there is a certain amount of kinetic energy at the start. So in fact, when you throw something up, the kinetic energy at the start is at the maximum because you are giving it a push, right? You're giving it a push for it to go up. And of course, this position, your GPE is the lowest because it's the lowest point. And as the ball goes up, it will start to slow down. And the reason is because gravity is trying to pull it down. So even though you have given a force to push it up, but gravity will continue to pull it down, slows it down. So as something is moving up, it actually slows down. Okay, so as it slows down, the speed gets smaller and smaller. The kinetic energy also becomes smaller and smaller. But at the same time, the ball is going higher, so GPE will increase. So whatever lost in KE will be the gain in GPE. And eventually, when you reach the highest point, this is when KE is equals to 0, because at the highest point, the object or the ball is not moving, right? So when you throw something up, when it reaches the highest point, it actually stops momentarily before it falls down again. So at this highest point, there is no speed. V equals to 0. So kinetic energy equals to 0. And as the ball drops downwards, um, again, this is the highest point, right? Because it's dropping. So your GPE is at the highest maximum value, but the KE is 0. Either it is being dropped, or the ball actually reached the highest point. Either way, it will stop. So the kinetic energy will be 0. Then slowly, as it moves down, the gravitational potential energy becomes smaller and smaller, and KE becomes bigger and bigger. So just before you hit the ground, kinetic energy is the maximum, and GPE will be the minimum. So it's very helpful for you if you could just remember that any upward movement, sorry. So if you throw something and it goes up freely and falls down freely, then going up is from KE to GPE. Coming down is from GPE to KE. Okay, so it will help a lot to remember this conversion, because it will help with questions like pendulum, roller coaster, and things like that. But do take note that it will be a different. Now, this is what we call a free, in a way, you can say that it's a free kind of movement. Okay, the movement is free because after you throw it, then you are not going to do anything. The ball is making the movement all by itself. It will not be the same. You can't say it's when you move the thing up, it's GPE, sorry, KE to GPE and so on. This will be a different scenario because this is not a free movement. You are actually controlling the movement by your muscles, right? So in this case, the movement will not be the same. So you have to read the question whether you are moving it up with an increasing or decreasing speed. So this is only valid. So this part here is only valid if your object is falling down freely, just dropping, or if you are just pushing it up and then you just let go and let it move on its own. Okay. In your slides, you will have the QR code for this very interesting simulation application by PHET. I will really highly encourage you to take a look and to try out the activities inside, because it shows very clearly how KE and GPE converts from one form to another. And if you were to change the setting to include friction as well, you will see that some of the energy will be lost as heat. And so what happens, when there is friction? Does it mean that GPE is always converted to fully KE? Which is not the case, because when there's friction, some energy will be lost as heat. If if this up and down motion, if GPE is always converted to KE and vice versa, then this skater, when he starts to skate from this point, he will go up, reach here, come down again, up, down, up, down. It will always forever be at the same height. But we know this won't happen because eventually he will stop. He will move to this point, and then this point, and this point, and then he just stop. And this is because some energy has been lost as heat due to friction. Final example will be a girl on a seesaw. This same explanation you can also use for pendulum, because pendulum simply means it's the same setup, except that instead of a human, you have a metal bob. Okay, so again, when you are on a seesaw, there will be two endpoints. So in this case, the endpoint is A and C. At these two endpoints, it doesn't matter where you start moving, but at these two endpoints, you need to remember that the speed is equal to zero. Therefore, kinetic energy is zero. This point and this point. Because when the seesaw goes to the end point, it actually stopped moving for a moment before it starts to change direction and come down again. Okay, so Ke is equals to zero. However, even though kinetic energy is zero at the two endpoints, uh, the opposite can be said about GPE. So at the two endpoints, your GPE is actually the maximum because it's the highest, right? The endpoints are the highest point. So GPE equals to maximum. And when the seesaw is slowly moving down, the speed actually increases. So it becomes faster and faster and faster and faster until it reaches the middle. Now, this middle point here is when the speed is the fastest. This is one thing that a lot of students make a mistake. They tend to think that the speed may be faster somewhere here or even just after A. But actually, the fastest speed is when it's in the middle, because as it moves down, it gains speed, and the fastest is here. Now, why is that so? Because right after the center point, then this seesaw or pendulum will start to slow down because it's moving upwards already. So any upward motion, remember, if you're moving upwards, you are going against gravity. So this part, your speed slows down. Okay, so with that, you can take a look at this example. And I think I have explained in the earlier slide about the KE and the GPE. And let's take a look at the energy conversion. So from A to C, you can see that, remember, this is like a free movement. You just let go. Unless this will not be valid if a person keep pushing um, the girl. All right, but if the girl is able to just relax and let the thing swim by itself, then this whole energy conversion will work. So again, this is like a downward motion. So remember, just now we said all downward motion. So this is the sorry. So this is all the downward motion. This is the upward motion. So downward. So all the downward motion is from GPE to KE. All the upward is from KE to GPE. So it applies even for a swing. So downward is from GPE to KE. And upwards, when it's going from C to E, right, is from KE to GPE. And the same thing apply again, because later on it's going to go down and up again. Okay, so this shows how energy is converted from one form to another. So basically, in the whole chapter that you have seen how energy is transferred when work is done from one body to another. You have also learned about energy conservation. So energy cannot be created or destroyed. It is only converted from one form to another, or transferred from one body to another. So it can be from kinetic energy of the person to kinetic energy of the javelin. So that is transferred from one form to another. You have also looked at some energy conversion from a few common household equipment or equipment that you see that is familiar to you. Okay, so we have come to the end of the work and energy lesson. Hope you have learned from here. And if you have any other questions, please feel free to go to your teacher. All right, so thank you very much. Happy learning.